Okay, so let's talk about atomic operations and variables. So we're going to talk here about what atomic operations and variables are, and we'll also talk about how to program them correctly. And this is a very low-level part of Java, but it's an important part of Java to understand, and more generally concurrency to understand, to motivate why we even need any of this stuff in the first place. So there are three key concepts associated with atomic operations and variables. And you can take a look here at this blog posting for more information about all these things. The first concept, which is really at the core of everything, is atomicity. And that really deals with defining actions and or sets of actions that have to be executed indivisibly. In other words, all or nothing. Here's a simple example that doesn't have atomicity. This is non-atomic operations. And you see we have this class with a couple of methods, increment and decrement. And I don't show all the code, but you get the basic idea. We have some integer counter, and this thread in thread T2 is going to run, and it's going to increment, and thread T1 is going to run. It's going to decrement, the same thing. And because those calls are not atomic, you know, who the heck knows what the values are going to be when you're all done, because they're all going to be scrambled up. So that's an example of not having indivisible steps. If you recall when we talked earlier about synchronization, I showed you how incrementing a counter by 1 or decrementing a counter by 1 is not actually atomic. It involves multiple steps because you have to read the value from memory into a register, increment the register, and then write the value back out to memory. That's multiple steps, at least 3 steps. And so that will not be atomic unless you do, of course, something to ensure it's atomic, as we'll be talking about in a second. The second issue here is called visibility, which determines whether the effects or when the effects of one thread can be seen by another. And by default, if you don't use anything to ensure visibility, then stuff won't end up being propagated in a timely way, in a correct way, to other threads. So let's take a look at a simple example. In this example, this is a class called loop may never end, which gives you a sense of what's going to go wrong here. So here we have thread 2, which is sitting there in a loop, checking to see whether or not this value is ever set to false, and it'll stop when it's set to false. And then we have another thread called T1, and it's going to be calling stop work, which will set the value of done to true. And depending on, this particular code is full of bugs, but depending on how the compiler works, it might very well decide that there is, in fact, nobody who sets this value in this thread, and therefore it could optimize this loop and just loop forever. It just won't even bother checking that condition. So this code, which is sort of incorrect code, even though it's kind of hard to see when you first look at it, this code is incorrect because it's not directed how we're going to propagate the set of this variable that's done here, the write of this variable, to the read that's done there. And so this loop might never terminate because it's, even though we make a change here, that change need not become visible. Now, you'll see how synchronization mechanisms and atomic operations can ensure that those things take place properly. But by default, if it's just a regular old Boolean, it might not be ever visible, or it might be visible much later in the program. And then the third thing is called ordering, and that determines when the actions in one thread can be seen to occur in order or out of order with respect to another thread. And this is kind of a combination of the visibility thing, but it's really about the ordering in which things take place. And on modern hardware, read and write operations can actually be reordered by the hardware, depending on where you're reading and writing to in memory. And so the underlying hardware may decide to allow reads and writes that were written in a linear order in your program to show up in other threads in the system in different orders. And it's up to the hardware to decide when and how to do that, based on all kinds of things like caches and where the memory is located physically and so on. So if you do not do anything to the contrary, you might have sort of thread 1 and thread 2, and in this piece of code, we start out with A and B being set to false, and thread 1 will set them both to true. And then when thread 2 runs, then if it reads B and A, it might read the value of B here. Even though this B is set after A, B might actually get propagated here first, so it could read true for that. It could read false on this read of A, even though that's in a different order. And then at some point, shortly thereafter, A might become true. And so these values could be set sort of arbitrarily to true or false, not to just random numbers, but to true or false. And those values would be propagated through the memory system in a way that's not in order with respect to the way in which you called them in that thread. So the hardware and the operating system and the virtual machine and so on are free to reorder all these things without requiring the program to be considered incorrect. So those are the three main things that we are going to be concerned with in all this discussion. Now, the same thing's going to be used, or the same basic techniques are going to be used to fix all these problems. It's going to have to do with marking your variables or your code in certain ways to ensure that stuff happens in the right order, at the right time, with the right visibility, and atomically if you need to. So all those things are going to be handled by the mechanisms we'll talk about. So as we said before, atomic actions basically have this all or nothing property, and so that means that changes to a variable are always made consistently in a manner that's propagated properly to other threads and will be done in an ordered fashion. So those are the things that happen when we use some of the mechanisms we're about to talk about. And you can read more about those mechanisms here. So basically the idea, it either happens at all, it happens all at once, or it doesn't happen at all. An atomic operation cannot stop and leave things inconsistent from the point of view of the outside world. Internally, inside the atomic operation, there may be brief periods where things are inconsistent, but the outside world won't see that, because by the time anybody can be in a position to check, the values will have been flushed out and they'll be available in the memory system in a consistent way. And the side effects aren't visible until the action completes. Like if you increment a variable, then when it's atomically done, that thing will show up altogether. The example we talked about before for atomic operations is the transporter beam. You obviously don't want to stop halfway through and leave a person in an inconsistent state. That would be bad. Horrible things would occur. I'm trying to think if that ever happened. That was probably a plot in some Star Trek where people got stuck in the transporter beam somehow, but that would be a bad thing, a malfunction. Oh, I guess, yeah, there's actually a link about transporter accidents, so you can find out about transporter accidents that occurred on Star Trek. All right, so let's talk about atomic operations. These are the most fundamental things that take place, and they're supported at the Java concurrent programming level by way of a bunch of features and optimizations that occur at lower levels in the stack, right? So you get them through either the virtual machine or in some cases through mechanisms even higher, but it's typically done through the Java virtual machine in conjunction with lower layer stuff that's available usually at the hardware level. So let's talk about some of the most fundamental atomic operations. One of the most famous ones is called a CAS, which stands for compare and swap. And you'll see, we'll take a look at some code in a second, but I'll walk you through sort of the pseudo code for how all this stuff works. You can read more about compare and swap here. So the idea here is you're going to call compare and swap, and you're going to pass in three values. You're going to pass in a memory location, a memory location, which is a pointer to something else, right? So it's pointing to someplace, to a value. And then we're going to have an old value and a new value. Those are the three parameters that are passed to compare and swap. Now, there's sometimes also another parameter we'll talk about later that's used in Java, but don't worry about that right now. So you're passing a memory location, an old value, and a new value. And what's going to happen here is within this region, starting here and going to there, and this would typically be implemented in hardware with hardware assembly language instructions that are provided by the processor on the system. What will happen is it'll go ahead and grab the existing value that's stored at the location that this is a pointer to. So it'll store the old value, and it'll check to see if the old value equals the value that was passed in here. And if those things are equal, if and only if those things are equal, is the location set to the new value. So that's why it's called compare and swap. And actually, it doesn't really swap. It's really more like compare and overwrite in some sense. But it's going to return the old value. So what's going to happen is you pass in this stuff. This is the location you care about. If and only if the value is equal, then you update, and then you return the old value. So you can find out what the value had been previously. Okay. And that's all done in an atomic region. So let's take a look then at how you would use this thing. So here's an implementation of a lock mechanism, like the kind of thing you get with the Java synchronized statement, or synchronized method, or a reentrant lock, etc. So this is something where we want to check and we want to lock something. We want to set it to be locked. And so what you do here is you pass in the location that you care about, and while the location's value is not able to be, while the old value is 1, then you keep looping. So here's how you read this thing. So remember, loc is the location in memory that we're interested in. I'll draw a picture here. So here we have a location in memory, and loc is a pointer to that location in memory. And what we're going to do here is we're going to go and we're going to check to see what the current value of this location is. If this value that's in here has a 0, that means it's unlocked. And so we're going to pass in a 0, and that's the value that we want to have it be. And this is the value we want it to become. And so you can see here, if the current value, go back, slide, if the old value, which is what it had already, equals old value, if the current value equals the old value, then set the location to the new value. So down here, what we're trying to do is we're saying, this is how you read this in English, if this is unlocked, lock it. That's what it's saying, right? So if it finds it 0, it replaces the 0 with 1. And then it'll return the old value. The old value would have been 0, right? So what this is doing is it's saying, as long as this thing is 1, in other words, as long as it's locked, keep looping. So what is the name of this kind of a loop? What's the name of it? Starts with a B.
Binary.
It is binary, though. You're right. It's a binary check, but it's a busy wait. So this thing's going to sit here, and it's going to spin until this value changes from 1, which means in use, back to 0, which means available. So 1 means locked, 0 means unlocked or available. And so this busy loop, this busy wait, is going to loop here until it gets changed back. Now, what's good about this? What's good about the fact that it's going to sit there and spin? Under what conditions would that be good?
If we wanted to start doing something as soon as it possibly can.
Exactly. So this is basically polling, right? It's polling the thing repeatedly. And so as Dylan said, the second, the nanosecond this thing switches from in use to available, we're going to go ahead and lock it right away. So that makes it fast. So that's one thing. It's very quick. So under what conditions is this going to be good?
Low contention.
Low contention, right? So if very rarely is this lock held, then this guy's going to come in here, and if the lock is rarely held, then it's going to take just a handful of instructions, right? It's going to start this atomic region, do the check, set the value, undo the atomic region, and we're done, right? So it's really super fast. So this is a good example of what's called a spin lock, or a busy waiting. And under low contention, it's a big win. Now, what happens if there's high contention? What if this thing is locked most of the time?
You waste a lot of processing time.
Right, you're sitting there spinning, and you'll go nowhere, right? You'll just sit there and spin. So you'll see that a lot of the Java stuff, a lot of the Java synchronization mechanisms we'll talk about, the higher level ones, reentrant lock, stuff like the semaphores and so on, they first try to do this compare and swap thing, and only if that doesn't let them in right away do they then go and do a sleep lock. And that way they are fast if there's no contention, and if there is contention, they don't waste time just spinning. Okay, so that's basically how that works. You can read more about that here at spinlock. And then unlock is really simple. All you do is the code would do some atomic section, however that's done by the hardware, disabling interrupts or whatever thing the underlying hardware supports, and it sets the location value back to 0. So that's unlocking the lock. Okay, any questions about that? There are other mechanisms I will not go through here. You can read about them. Another mechanism is called test and set. And you can see in a nutshell, it's very similar to the other one. What it's doing is it's going to go ahead and read the old value and set its value to 1. And you basically just keep looping until this thing basically no longer is true. So it's much the same idea. Some hardware supports test and set. Some supports compare and swap. Okay, so that's the low-level mechanisms, and almost everything that is done in concurrency sort of ends up reducing to that, right? But that obviously is inefficient, so we have to build all kinds of other things on top of it. And I mean, not only is it inefficient, but it's also hideously complicated to program in the sense that it does a very simple thing. It's very simple at one level, but it's very complicated to reason about at a higher level. So everything else basically takes those building blocks and then adds all kinds of other cool stuff to it. So one thing that's actually provided in Java, by the way, what I just showed you, of course, is not Java. It's C code. But one thing that's provided in Java is something called compare and swap long. And that's actually in a class in Java that's called Java Unsafe. And the unsafe class is basically intended to be used by people who are Java infrastructure builders, the people who built the Java class libraries, the frameworks and so on, the virtual machine. This type of thing is meant for them. They're not really meant for average application developers, which is why they're unsafe. They're meant for people building the low-level infrastructure to provide the higher-level abstractions. And of course, it's also provided because there are people who want to use the Java virtual machine for non-Java languages, so Scala or Clojure or so on. Those are languages that are run on top of the Java virtual machine but are not themselves Java. So compare and swap basically is a variant of what we just saw. And under the hood, it actually uses those low-level mechanisms, but it provides them through a Java interface. So here's the way this works. Compare and swap long atomically sets a memory location at an offset from an object. So unlike what we saw before, where we had 3 parameters, this time we have 4. We have the object, which is just a good old-fashioned Java object, the offset of the field from the beginning of that object, which is kind of a low-level thing if you think about it, and then the expected value and the updated value. So you basically, it's going to do this check, and we'll see this in a second. You can actually look at the code if you want to see how the code works. It's pretty cool. So here's how this works. Atomic long, yeah. Because
an offset from an object.
Good question. So when you have an object in Java, like class foo, inside of class foo you might have int a, long, b, char, c, etc. And in your code, when you say something like, foo f equals new foo, then, if there's f is going to basically be laid out like this in memory. It'll have an int field, it'll have a long field, and a char field, or something along those lines. So if this is offset 0, which is the beginning of f, then this would be, f plus the offset in bytes. So if this is an int field, then this will be 4, right? So b will start at f plus 4. So that's just basically how the code is laid out in memory. So that's what an offset is. It's just it's a count in the number of bytes from the beginning of the object. And if you think that's rather low level, you're right. It is. It's intentionally low level. So this is what the code would look like. So atomic long, which is the grad students have to implement this for the assignment. Atomic long has a volatile long, which is the value that's being atomically incremented and decremented and so on. And then the get and increment method turns around and calls unsafe get and add long. And what that does is it's going to take this, which is the object that this thing's being called for, the value offset, which is going to be, whatever the room it is from the beginning, whatever the field is from the beginning of this thing, which is probably going to be like 4 or whatever, and then what we want to set it to, which in this case is the value 1. And so decrement does the same thing. Unsafe get and add long. To decrement, you simply add -1. To increment, you add +1. To decrement, you add -1. And then if you take a look at get and add long, if you were to go inside and look at the code inside get and add long, what it basically does is it goes ahead and takes the object, which would be whatever the atomic long is, the offset which is whatever the field is, the field being the value offset. I'll show you how that gets set in a second. And then whatever we want to add or subtract to the thing, and it goes into a loop, and while compare and swap long, which is just the low-level, unsafe way of doing the compare and swap algorithm we just looked at. It's going to go ahead and go to this offset from the start of the object, and it's going to check to see whether the value equals v, which is the old value, and then we're going to set v to v plus delta, which in this case would be 1 or minus 1. So that increments or decrements by the appropriate amount. So when the value equals this, it gets set to that, which is super cool and super efficient. Okay, here's how the value offset gets set. If you take a look at atomic long, it actually uses Java reflection, and it goes and it looks up inside this class, and it finds the offset inside the class of the field with the name value. So it goes up and it looks and it finds that, and it stashes that away, and that's what's going to get added when it goes ahead and calls the offset here. Now again, that's super duper low level stuff, but it's kind of cool to see how it works. Okay, so those are the very, very low-level basic building blocks. So what I just talked about was the hardware-level operations, which are the compare and swap, and then Java provides you with a class called the unsafe class, and it provides software-level portable wrappers to whatever hardware-level features are available that do that thing on the bare metal. And then other parts of Java come along and provide layers of abstraction on top of that. So given that, now let's talk about volatile variables, because they relate to this in some ways. So volatile, if you recall, ensures that changes to a variable are always consistent and visible to other threads atomically. So it's an atomic operation, but it's just a read or a write. So the idea here is that reads and writes on a volatile go directly to memory. Do not pass go, do not collect $200, go directly to memory, and they avoid conflicts that we had talked about before. The other thing that this says, and this is when you mark something as volatile, this has to be handled by the underlying implementation. It says that the compiler, the runtime system, the hardware, and so on cannot reorder reads and writes. They have to go in a strongly ordered manner. And that avoids those problems we looked at before with ordering. So if something goes before something else in the sequence, then those values have to be pushed out first. Now, under the hood, reads and writes to volatiles are automatically transformed by the compiler, by the virtual machine, et cetera, into acquire-release pairs. In other words, acquire something to ensure that you can get atomic access to read or write, and then do the thing that you're doing, read to it, write to it, or whatever, and then release that. So those things are transformed for you automatically. And that transformation, by the way, may take place very low level down in the stack. That's probably going to be turning into like bytecode level instructions that do this stuff to handle those kinds of operations. Now, in a sequential program, that is a program that only has one thread, you don't need any of this stuff because it has full ordering, because there's only ever one thing happening, right? You're reading and writing, and you're only in one thread of control, so it's only going to be dealing with one cache, one processor, and so on. And a good example I always like to think about sequential processing is like a FIFO queue, right? Like a taxi stand at an airport, or going through a drive-through at a fast food restaurant, right? Just going through things in line where you can't cut ahead of somebody. Reads and writes of most Java primitive variables are atomic. So if you have something like an int or a character and you read and write to it, those operations are atomic. And it's really things that are on 4-byte boundaries that are done atomically. However, longs and doubles, which are typically 8 bytes, require multi-step operations. At the Java bytecode level, those are multiple operations because they span the 4-byte boundary of ints and characters and shorts and so on. And so we'll take a look at some examples to illustrate how all this stuff is going to work. In concurrent programs, you need to have volatile if you don't want to have your programs be full of bugs. So here's the reason why. The problem is if you don't use volatile, then one thread may not see the latest value of a variable changed by another thread due to caching that takes place in the memory system of whatever processor chipset you're running on. Now keep in mind, this is pretty low-level stuff, and we're trying to provide a high-level programming abstraction that is ultimately accessing very low-level things. So here's an example. So this is the way that we're going to show the problems. Here's main memory, right? And then we have these different threads or processor cores, and each of these processor cores has their own cache. So we might have up to n of these caches, right? And at the moment, here's main memory. At the moment, everything's consistent. We have the value of 42 and the value of 13. NV stands for non-volatile, a non-volatile memory object like int A. V stands for a volatile memory object, which would be something like volatile int B or something like that. So this is the current value. Everybody's got everything cached properly. All right, so now somebody comes along in this thread and writes the value 7 to a non-volatile memory location. So 7 is stored in some thread, you know, A equals 7. And the problem is that if shortly thereafter another thread reads the value of NV, it will get an inconsistent value because that value has not been propagated through here. So we started out, we wrote to this thing, and that will not be propagated properly. So by using volatile, you can avoid these problems. So let's take a look at this. So in this case, if we write to a volatile variable, then a couple of interesting things happen. First of all, the non-volatile guy gets flushed out as well, typically, because they're usually on the same cache line. They don't have to be, but they could be. So in this particular case, we write to the volatile variable. That updates both the non-volatile and the volatile, but that's sort of random, right? You're not supposed to count on that happening. It just happened in this case. So the value is written through the cache into main memory, and a volatile write happens before all the following reads of the same variable. What that means is that the reads and writes are ordered properly in the memory system. So that means over here, when we come along and we read V, that will go ahead, in this particular case, notice it's also having an update on the value of the non-volatile variable, but that you can't rely on that. That's just happening because of the implementation. Over here, we're going ahead and reading the value, and that then turns out to be the right value. And likewise, if this guy in thread N was to read, it would also get the latest values. So volatile reads are cheap. If you're reading a volatile variable, boy, is it cheap. It's hardly anything at all because you're just going and getting the value from memory. That's all it's doing, really, just going to main memory and reading the value. So it's super cheap. Writes are a little bit more expensive because we've got to go ahead and write the value to main memory and then propagate it out to all the caches, right? So that's a little bit more expensive, but that is still cheaper than using Java synchronized statements. So if you try to nest all of your fields in synchronized blocks, it would be, first of all, be hideously ugly to write, but secondly, it would also be less efficient than if you use the built-in mechanisms. Yeah?
Don't some processors have shared caches so they could avoid going to main memory every time?
Oh, sure. But you wouldn't want to make every write update all the caches either, right? I mean, an implementation could do that, right? You could have, you would typically have something like that if you had non-uniform memory access, where it would take a long time to go to main memory. So you might have, like in a distributed system, for example, you would push out the values to all the parts of the system that needed to be aware of them, which would be potentially cheaper than going to the central core all the time. But same principle still applies. You don't want to do that for every operation. That's how you might implement a volatile-like thing in a distributed system, though. So atomic reads and writes are atomic for all variables, not just the ones that are like, 4 bytes or less. And this is the thing that talks about this. So reads and writes are atomic for all variables declared volatile, including longs and doubles. Reads and writes are atomic for variables and primitive operations, except for longs and doubles. Reads and writes are atomic for all variables declared volatile. So you can read more about that here. So volatile also does a few other things. It also guarantees visibility. We've talked about this example before when we talked about volatile. So here's a case where we want to make sure that the code that we show here, which is where we're defining this as a volatile, this, if T1 writes true to M is stopped, the next time another thread reads from M is stopped, we want that thing to be set up as being true. Hi.
You guys are looking for room 132, feathering y'all.
This is probably not the right room. What's it for? I know, I was going to say free food is great, but...
Connie Smith, room 132.
Let me see. Feathering Hall, room 132. That is too funny. I'll tell you where we can go. If you here, just come through here, and I promise we won't steal your food. Anybody know who Connie Smith is, aside from being a country music singer? Who sang, what was her famous song? God, I can't remember it. You might go check over there.
Okay.
In that little room. That's where they have people. Oh, all right, we found her. Sorry, I thought we had free food. What's her favorite hit?
Once a day.
Oh yes, that's right. That's right. I saw her. I think she might have died recently. She played at the Grand Ole Opry a couple years ago. I saw her performance, and her song, his song, it's like a country music song, so it's about heartache, right? And the thing is, I only think about you once a day, all day long, right? That's the. That's a very long critical section, right? You know, you don't release the thinking about you lock for a long time. It's exactly. That's great. We'll work that in. So the idea here is that when this guy sets M is stopped, the values propagate to all the caches or to all the other threads, so that when they go ahead and read, they get the latest value. So that means it becomes visible. That's visibility. So the volatile write here is visible to happens after reads. So in other words, the write happens before the reads. Volatile also guarantees the ordering, same basic idea. And so this basically says that these things get done in the right order. So the write to M stopped in T1 must happen before the T2 read completes. Okay, just to reiterate, volatile only gives you atomicity of reads and writes. It doesn't give you atomicity of operations on the variables. So incrementing a volatile is not atomic. So even if we have some volatile value, if we go ahead and do, like, you know, volatile value plus plus, and we do it in two different threads, this is what you would end up seeing. You would see the value being read into the other threads. We're increasing the value by, you know, whatever, I guess 1 or 2 or whatnot, and then it gets written back out. And those things are different operations, so they might actually screw things up and you get the wrong value, even though any one of the reads and writes would be atomic. These guys would be atomic, but this stuff, there's multiple operations here. So bottom line here, if you need to have atomic operations, then the best thing to use is the higher level primitives in Java, like atomic long or atomic integer or something like that, because those give you those features, and you don't have to, well, they come for free, unless, of course, you're assigned to write them, which is what the grad students have to do for the next assignment. So if you don't write a concurrent program correctly, then the problems you have typically fall into one of three things: atomicity, visibility, or ordering at this low level of abstraction. Right? So when you're dealing with the low level of abstraction, there's typically three things that go wrong if you don't properly synchronize your code. Now, there's also lots of other kinds of problems that happen as well, but these are the three things that happen at this low level. Okay, so let's show some examples of using volatile in practice, and this will illustrate a whole bunch of interesting things, including some rather cool patterns. So this particular example is going to illustrate how to ensure atomic reads and writes very inexpensively. And the idea here is we're trying to come up with a way to synchronize a singleton. Does everybody remember what a singleton is? We covered that in the earlier classes, but if you didn't take the class or you forgot over the summer, let me just go over this real quickly. So imagine that we have a class like this. We have a singleton. And the idea here, if you recall with singleton, you have a method that's a static method, and it would look like this: static instance, and it's going to do some stuff. And then you've also got a static data member, which we'll call M instance, for lack of a better term. And let's say, you know, whatever static T, whatever we need this to be. Is it a, you know, integer? Is it a long? Or whatever the thing is, it's an instance. So that's what that looks like. So the typical behavior you have in a regular old singleton is you have code that looks like this. If m instance is null, then go ahead and set m instance to new t, whatever t is, and then in either case return m instance. So that's sort of your classic canonical singleton. But there's a problem here. Can anybody spot the problem of the singleton when we get into multi-threaded situations? What could go wrong?
Two threads might be inside the if loop at the same time.
Right. So the problem with the default implementation of singleton is if two threads get into instance before it's been initialized, they or actually n threads for that matter, they might all find that instance is equal to null, and then all of them would go ahead and make a new t. And then some variable, some implementation of t will eventually propagate somewhere, and in the meantime you've created all these extra t's and it's unclear what the value is at any given point in time. So that would be a horrible situation. So that would be bad. So what would be one way to fix this? What would be the simplest fix for this? Monica? Right. So we could put, static synchronized, or we could put a synchronized block or whatever, right? So that would be one thing to do. Okay, so that'll work. Now we have a synchronized singleton accessor method. But what's wrong with that code? What's the limitation with that code? Right, so what's the condition under which we don't need there to be that? Right, so this solution is excessive. So before, if you didn't have synchronized, it was not enough synchronization. It's kind of like Goldilocks and the Three Bears, right? This is too little synchronization. This is too much synchronization. And the reason this is too much synchronization is because we only need to check for null before it's initialized. Once it's initialized, we don't have to check anymore. I mean, we don't have to do that check because this will never get run. This should only get run one time, and afterwards it should always be true, and so therefore we'll always just return the old value. So this is too much synchronization. So the trick is to have just right? We want just like Goldilocks. I want my porridge just the right temperature or whatever. Okay. So here we have the static singleton, or the class, and I'm going to show you how you can use Volatile in order to get just enough synchronization. And this is actually a pattern called the double-checked locking optimization pattern that I wrote many years ago and has led to a whole bunch of interesting discussions. If you want some fun, read the Wikipedia article about that. But I'll show you how to do it in Java. All right, so what we do here is we end up using a volatile variable, as you can see here, private static volatile singleton inst. That's called inst, which we set equal to null. And when we come in here, what we do is we set inst to a local variable called result. And then we check. And if result is null, in other words, if this is the first time in, then and only then do we go ahead and do a synchronized. And what we're doing here is we're synchronizing on the class itself. So when you synchronize on a class, unlike synchronizing on this, well, what's the difference between synchronizing on this versus synchronizing on the class?
When you're synchronizing on this, you're synchronizing on that instance of the object. So
Right.
other instances could have different.
Yep. So if you have, in this particular case, there is only one instance, but let's leave that aside. In general, if you synchronize this and you have multiple objects, then each of those things are distinct, right? But here we want to be able to have the one and only place to synchronize, and that's the class itself, because there's only one instance of the class, right? So this will synchronize on the class monitor lock, but only if this is null, in which case it'll then go ahead and, as you can see, once it synchronizes, then with the lock held, it'll go ahead and double check. So then it'll take inst again and check it again, and if the result is still null, then it goes ahead and it makes a new singleton, and it assigns those things, and it returns that. So this only happens the first time in. And after the first time in, result will always be non-null, And so any other threads that come through will notice this, and they'll skip over and just return the result.
Well, why do we need to reset result to inst again?
This is just a little trick that the Java people put in order to make the double-checked locking thing work properly. It's kind of a hack, and that's why if you read this article, there's a lot of vitriol about double-checked locking, and it's a bad thing, and so on. But it's actually not a bad thing. It just has to be. You have to understand how it works properly in order to use it, and this is how you use it properly in Java. And the way this works is that we have volatile read operations. So this is a read. This is volatile read. So that's going to be atomic, right? And this is a volatile write. So that'll be atomic because this is a volatile variable, right? So that's a read of a volatile variable, and that's a write to a volatile variable. And those things end up being atomic, and therefore we get the right behavior. So it's to amuse yourself, you should read all the vitriol about this. It's kind of like double-check locking is the go-to of synchronization, right? People get all bent out of shape about it. But it turns out to be a remarkably useful idiom, and it's used all over the place in Java and C++ and operating systems and other places. You just have to be very careful in how you use it. Okay, so let's talk a little bit about these atomic operations. Concurrent applications should use these operations very carefully to avoid busy waiting or spin locks, right? So you think of a gerbil or a hamster running around in a wheel, right? It's going really fast, but it's not going anywhere. Typically, you want to hide this level of stuff, these atomic operations, in libraries that abstract away from all this low-level stuff and give you much higher level abstractions. A great example of a much higher level abstraction that under the hood relies on all this stuff is the implementation of concurrent hash map. If you ever want to just completely lose your mind, read the code for concurrent hash map, which is unbelievably complicated, really cool, but unbelievably complicated to write. And under the hood, it's using these spin locks, the compare and swap type of thing, in order to be able to allow lots of threads to be simultaneously looking stuff up in the hash map without interfering with each other. So the hash map is a way of actually spreading out. It's reducing, basically, contention for synchronization mechanisms in multi-core systems. So you don't want to write that code, but you can use it because you've provided a higher level of abstraction. But you needed compare and swap to make concurrent hash map super duper efficient. And to learn more about this, I highly, highly, highly recommend you spend an hour, or however long this thing is. It's about an hour, I guess. Take a listen to this lecture by Doug Lee. It's an audio, it's a screencast, so it's him talking and flipping through slides. He talks about engineering concurrent library components, primarily focusing on Java, but could be more broadly applied. Really, really great talk. It just blows your mind. I've known him for a long, long time, and he's done a lot of great stuff. He's written most of the concurrency mechanisms that are available in Java util concurrent. So almost everything in there, if you look at the author list, he's the guy who did it. Amazing, amazing understanding of this stuff, and he really explains in detail how it all works. So complex operations that perform multiple steps can't use volatile by itself. So here's the example, right? The counter thing that we saw before, because those are actually multiple instructions. So you'd increment, and that takes several steps, and so on. And we saw before that's going to cause problems. So instead of using, a naked volatile, which is not good, instead use something like an atomic long or an atomic integer. And that gets you the same basic, it's about the same amount of code to write, right? Instead of saying volatile int counter equals 0, you say atomic long counter equal new atomic long 0. That's how you initialize it to 0. And then instead of saying counter plus plus, you say counter get and increment. And that does all of these things, but it does them all atomically. So it's easy to use, but also very efficient. And it's super efficient as well. There are some limitations with volatile. Making something volatile only makes the reference volatile. It doesn't make the thing it points to volatile. So you have to be very careful when you use things like arrays and so on, because the individual elements in them are not actually protected, just the reference itself. So here's an example where the vector reference is volatile, but the elements inside here are not volatile. Now, if you want that, then you would have to either use something like a synchronized keyword, which is what they do in array to do this, to protect that stuff, or you would use some of the atomic arrays that are built into the Java atomics package. Another thing, this is sort of a side note, I won't spend much time on it, but C++ and C also have the concept of volatile as well. And sometimes people think that C's and C++'s volatile semantics are the same semantics that Java has. That's not the case. In C and C++, volatile doesn't give you atomic behavior, and it doesn't give you the happens before relationship. In fact, all it really does is it basically tells the compiler, don't optimize away the use of this variable, even though you can't tell easily where it's being set, because it may be being set like in an interrupt handler or something else like that. So it's really just a flag to the compiler to tell it certain things. And people always get confused when they move between languages what the semantics are. Okay. Any questions about any of that stuff?